4.1 Organized Counting. So in 4.1, we will learn the techniques in mathematical logic for counting possible arrangements when choosing from a group of people. Real-life examples include such things as planning a starting lineup for, like, say, a basketball team, okay, arranging seminars, or ordering letters or numbers on, like, license plates or phone numbers. Okay, so we're going to start with tree diagrams. And this is the most basic way to organize numbers. So suppose you need to put together a funky outfit for Funky Outfit Day. You have 3 shirts to choose from, and then you have 4 pants to choose from, and then you have 2 different socks to choose from. So how many different outfits could you create? So we're going to start with the 3 shirts. So you can either choose shirt 1 to wear, shirt 2, or shirt 3. And now, if you choose shirt 1, you have 4 pants to choose from. So you could have shirt 1 and pant 1. You could choose shirt 1 and pant 2, shirt 1 and pant 3, shirt 1 and pant 4. Or you can choose shirt 2 and pant 1, shirt 2 and pant 2, and so on. Shirt 2 and pant 3, shirt 2 and pant 4. Okay, and the same for shirt 3. Okay, and now you have 2 different socks to choose from. So for socks, I'm going to use a K. So sock 1 or sock 2. So you can choose sock 1 or sock 2, which with each of these possible outfits, you can also then extend it into sock 1 or sock 2. So, for example, shirt 2, pant 1, sock 1, or shirt 2, pant 1, sock 2. Shirt 2, pant 2, sock 1, shirt 2, pant 2, sock 2. And we can continue going all the way down. So K2, K1. That's okay. These 2 are put backwards, doesn't matter. Okay, K1, K2, K1, K2, K1, K2, K1, K2. So if we're counting how many different outfits we can create from this tree diagram, what we actually look for is we look for the number of possible outfits. So like this would be 1 and then this would be 2. So every time in this last column there's a K, or like a K1, K2, every time there's an outcome in the last column, we consider that as one different outfit. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, and if we count these ones, again we get 8. And if we count these ones, again we get 8. And we only count the last column because this is one outfit, this is the second outfit, then this is the third outfit, then this is the fourth outfit. So this last column represents like the last piece of your outfit each time. So therefore, 8 plus 8 plus 8 is 24 outfits. Okay. When planning a trip from Niagara Falls to Ottawa, Betty wants to stop in Toronto and Belleville on the way. Okay, so we're going from Niagara Falls, we're going to Toronto, to Belleville, then to Ottawa. Suppose that there are 2 different routes that she can take from Niagara Falls to Toronto. So I'm going to call this T1 is the first route to Toronto, and T2 is the second route to Toronto, right? Like Niagara Falls is just her starting point, so it's going to be the same starting point. You could put N to Toronto 1, N to Toronto 2, but that N for Niagara Falls doesn't change. Okay, 3 different routes she can take from Toronto to Belleville. So first route to Belleville, B1, second route to Belleville, B2, third route to Belleville, B3. Okay, B1, B2, B3. Now there are two routes that she can take from Belleville to Ottawa. So Ottawa 1, Ottawa 2. Ottawa 1, Ottawa 2. Ottawa 1, Ottawa 2. Okay, same over here. Ottawa 1, Ottawa 2, Ottawa 1, Ottawa 2, Ottawa 1, Ottawa 2. So the question is, how many different ways can Betty drive from Niagara Falls to Ottawa? Okay, so we get 6 different ways here, 6 different ways here. So therefore, she can drive 12 different ways. The fundamental counting principle. So doing those tree diagrams for a large number of items can be quite tedious. So if we can use the fundamental counting principle instead of like actually drawing the tree diagram. So if a task or process is made up of stages with separate choices, the total number of choices is like m times n times p, and then keep going, times. So m is like the number of choices in stage 1, n is the number of choices in stage 2, p is the number of choices in stage 3. So let's redo examples 1 and 2, but this time using the fundamental counting principle. So in example 1, if you remember, we have shirts, which is our stage 1, and then pants, which is our stage 2, and then we have socks, which is our stage 3. So we have 3 shirts, 4 pants, 2 socks. If we multiply 3 times 4, which is 12, and then times 2, we have 24 outfits. Okay, much faster. Now, let's redo example 2. We have the routes to Toronto times the routes to Belleville times the routes to Ottawa. And I just short form these. So 2 routes to Toronto, 3 routes to Belleville, 2 routes to Ottawa is OTT. Okay, 3 times 2 is 6, times 2 is 12. So we have 12 routes. Indirect method. So in some situations, the indirect method makes calculations easier. So what we would do is we would take a look at what we're actually looking for, which would be like the successful ways. Okay, what we're looking for. You can make a note of that. What we are looking for. And how we're going to actually calculate it is not directly that you've seen in the last couple questions, but what we're going to do is we're going to take the total number of ways something can be arranged and then subtract the unsuccessful ways. Okay, when the unsuccessful ways is really easy to calculate, this is usually the approach that we take instead of something like way more complex. So in example 5, we take a look at the indirect method. Stacy has 4 pairs of running shoes in her gym bag. How many ways can she pull out 2 unmatched shoes, one after the other? And then we're going to use the indirect method. So what we're going to take a look at is the total ways she can pull out 2 shoes. So I do underlines throughout this course. So the first shoe that she has, so she has 4 pairs. So if you think about it, how many shoes does she have? She has 8 single shoes. So the first way that she can pull out a shoe is 8 different ways, because there are 8 different shoes. Then, how many shoes are left? Well, 7 are left, say, in the bag. So how many ways can she pull out the second shoe? 7 different ways. So this would be first shoe, and then and then this would be second shoe. And what we're going to do is we're going to subtract the unsuccessful. So the unsuccessful way of having unmatched shoes would be actually matching them in this case. A little bit backwards thinking, because you'd think, well, wouldn't you want in real life matching shoes? But that's not what the question's asking. So we want to take away how many different ways she can have matching shoes, and then that's going to leave us with how many ways she can have unmatched shoes. Remember, unmatched shoes is our success in this case. So 8 times 7, and then we're going to subtract. So how many ways can you have matching shoes? Well, you can choose any of the 8 shoes. But then if you think about it, there's only one shoe that matches that first shoe. So depending on whatever the first shoe is, you only have one way of matching that shoe. So that would be first shoe and then the second shoe. So there are only 8 ways that you can pull out 2 shoes one at a time and get them matching. And that's going to equal our number of ways that we can do unmatched. Number of ways to pull unmatched. Okay, so let's do 8 times 7. I get 56 minus 8, and I get 48. So there are 48 ways to pull out unmatched shoes. Okay, a lot easier to do the subtraction than to list all 48 different ways. So mutually exclusive cases. So when we have different cases that do not overlap, we have to use something called the additive counting principle or the rule of sum. Okay, when we think about not overlapping, we think about two different things can happen, and they're 2 completely different scenarios. They can't happen at the same time. Okay, and what the additive counting principle is if one mutually exclusive action can occur m ways, a second action can occur n ways, a third can occur p ways, etc., then all we do is we add them together, and this is like the total number of ways that these actions can occur. I call this, and if you want to jot this down, like cases when there are different scenarios, different cases. Okay, you can also write down different scenarios. Okay, so let's take a look at example 6, signal flags. And we're already starting to pay attention to the English language here, and we're already starting to decipher between what kind of words are triggering what kind of questions. So when sailing in a sea, boats use different combinations of flags to communicate. Okay, so how many different signals are possible if a boat has 4 distinct flags? So that's like 4 flags to choose from, okay? And a minimum of 2 flags are used for each signal. So when you think a minimum of 2 flags, we're thinking different scenarios here. We're thinking, okay, how can I choose 2 flags? But the problem is it says minimum 2 flags. So you can also think, how could I choose 3 flags as well? And how many ways can I choose 4 flags? Okay, there are 3 different scenarios, 3 different cases here that we have to consider. And then all we're going to do is add them all up after. So how many ways can we display 2 flags? So if we have 4 flags, we have 4 flags to choose from. And once we choose that one flag, we have 3 flags to choose from for the second flag. Okay, how many ways can we display 3 flags? Well, the first flag, we have 4 flags to choose from. Then we have 3 flags to choose from. And then there's 2 flags left, so we have 2 flags to choose from. Now, 4 flags. How many ways can we display all 4 flags? So, we have 4 flags to choose from at first. 3 are left. We have 3 to choose from. 2 are left, and we have 2 to choose from. And then we have to just fill in the last flag with whatever's left over. Okay, so 4 times 3 is 12. 4 times 3 times 2, we get 24. And 4 times 3 times 2 times 1, we get 24 as well. Okay, so altogether, there are 60 different ways to display the flags.